Good to see that there are at least a few people wanted to listen to this stuff about this bleeding edge modern technology that we use for crash and test failure analysis. So my name is Jan, and this is Thomas. We both work at Cisco Lysaker, so that's just west of Oslo. This is our office building, and in here we make these beautiful video collaboration devices. So if you were in the previous talk in this room, there will be a little bit of overlap. That's so the same company, same products. For us, with these products, just good enough is not really considered good enough. One thing is that we don't think it's a good idea for any business to skimp on the quality of their face-to-face communication. And another thing is that our products are often deployed in high-end scenarios like this, with high expectations and very demanding customers. So as you can imagine, delivering with the highest possible quality is essential for us. We also want to be nimble and fast, so we try to keep a tight feedback loop using a continuous delivery approach with minimal branches and rapid release cycle. So every single day we try to release software directly from our main branch to our latest channel. And once a month, one of those daily releases goes on to serve as the basis for a release to the stable channel that our customers will see. This is a pretty diverse product range with a huge feature set, lots of moving parts to test it. So it can be very challenging to be able to keep up this rapid release cycle and hit that quality level that we're aiming for. So today we're going to talk about one of the tools that we use for crash and test failure analysis. And that is essential really for us to be able to pull off keeping this tight feedback loop running. Thomas is going to talk about how we use it for test failure analysis later. But the story of this tool started 13 years ago, very modestly, when I tried to follow up with some crashes in our software. So let's head back to 2011. Products back then, not quite as beautiful. They were much simpler in some respects, but often internally, they were more complex, really. The way we delivered software for this was a lot less mature. And in particular, we did not have any systematic way of handling crash reports at all. But around this time, someone, I think maybe Henrik, set up automatic crash reporting from the devices to a central web service. And that service put the crashes together in groups into what it considered the same problem. The problem was that it didn't really work that well due to the complex nature of these products. And in particular for me, as a video guy, my software was running distributed across a number of video DSPs in these systems. And that fully automatic web service tool didn't even consider the log files that were relevant to me. So it ended up pretty much saying that all the different bugs that I cared about, that was the same thing. Didn't really work for me. And I didn't really have an intention to start any project to try to improve on this service or anything. I just wanted to get on with my job. So let's now imagine that this bug report here, Jira ID CE 94048, is assigned to me. This is just a screenshot from our current Jira trackers. It's not 2011, but it's a good example because it's an assertion failure, so it's an explicit abort where this text here basically says what the problem is, and that text is present in the logs, so it'll be easy to demonstrate. So let's imagine it's 2011. Before this, by the way, I would just work manually with it, download logs, maybe ask for logs, take a look at the logs manually. Very inefficient. But now that I saw that we had this data set, the data contained all the information that I needed. It was just that the automatic classification of it didn't really work. So what I would do was to head over to the terminal, and I would simply start copying the logs over from that crash service to my local machine. So I've prepared a folder here called crashes. Each of these numbers represents one crash report. We can take a look at one of them. It's just basically a folder structure with some log files. So in this scenario, I would want to find cases of this particular bug that was assigned to me. And I would simply then, on the command line, do something like this. So in the crashes folder, find some log files, pass them on to rep, so that I could use regular expressions to search for stuff. So I won't teach or say anything about regex syntax in this talk. I'm imagining most of you know it already. If not, there are resources. I'll just say that this .star thing means skip ahead some text. So what we're doing here is searching for the word get role compensated crop, then we skip ahead some stuff, and we search for the word assertion and skip ahead again, and so on. So if we run this, we'll see that there are a number of instances of that particular bug among these crashes. Now, this seems, of course, pretty backwards when you have a fully automated web service and doing this manually like this. But for me at that point, I was like, it was so much better than what I had from before, because now I could see like the frequency of the crash, the problem. I could compare the different logs to see if there are some clues there. Maybe I could see some pattern about what system types are crashing, stuff like that. So, of course, it pretty quickly became tedious to write those commands on the command line. And then you, of course, implement a small shell script. So, initial commit in that repository was April 2011. And then things sort of took off. So today, same repository closes in on 10,000 commits. So much for not starting a side project. Guess this is the longest running side project maybe in our department. Anyway, let's take a quick look at the early version of the script. Might want to brace yourself, this is not so beautiful. Essence here is that we've got a list of crashes, a list of rules. For each crash, we loop over the rules. We try to check if that rule matches the crash report. If it does, we output that match, and then we simply return. So this might seem a little bit silly, because you're just ignoring the rest of the rules, right? What if multiple rules match? Well, the result could be a little bit of a lie, but as I demo this, you'll see how that plays out, that particular choice. So let me head back to the terminal. So we're actually at the root of that repository here. This is maybe 25 commits in. So the script has a few more features, but it's essentially doing the same thing. So that's the ACR classify thing. Then there's a file called classification rules, which is the file that holds the list of rules. Got that open in a separate window here in an editor. So you'll probably then notice or recognize the highlighted part on the right to be that pattern that we searched for previously. The syntax for the script is really minimalistic, so the colon simply separates the pattern on the right from a description on the left. So there you see that Jira ID again. If we run this, oops, like that, you'll now see that it, at the bottom here, says classification summary. Then there's this description from the rules file. It says 10, which means that it found 10 instances of this particular problem. And then down here it says unmatched 32, so the rest of those crashes did not match. Up here, each section represents one crash report. So you can see that the last one is a case of that problem. These purple ones are not, and then there's one case up there again. So that was sort of the start of it, and already I started sort of just collecting patterns that I was interested in. But it pretty quickly also became clear that, well, what are these 32 other things? It would be nice to know if I could get all of them like this classified. That would be nice. So let's take a look at one. I want to find a file called crash.log. And at the top here, you can see that it says reporting crash in bin main. But I'm a video guy, right? So I'm not so interested in crashes in main. That's someone else's responsibility. So I could go on and take a look at the next and the next, see what I find. But I've got this list of rules here, right? So what if I do reporting crash in skip ahead video? And let's run it again. So now more blue cases. And at the bottom, you can see that it now says that it found 17 of them. That's helpful for me for now. I can just go up here and see here's a case. We can take a look at that. That's sort of making my life a little bit easier. So now we've got the video crash, and it says down here, signal zigzag, which means it's some sort of illegal memory access. There's a register dump, and then we've got a call stack here. Well, let's just say that if I could create a rule that would match this zigzag part and some relevant parts of the call stack, that would be a good way of classifying this particular problem. So I've prepared a little bit, run this nx command. I'll pull a rule for that into the classification file. So if I refresh here, you can now see that we've got a new rule with a new description, a new Jira ID, and it searches for the zigzag part, then another minimalistic syntax thing. The ampersand means I want another regex, and then a regex that finds some relevant parts of the call stack. We can run it again. So at the bottom here now, you can see that it found 2 cases of that particular thing. And up here is that case that we looked at. Now you can see that it has the description here and the relevant parts from the logs. So we could continue like this. That was what I would have done then, just get all the stuff classified. But let's stop for a little while to think about this, because the ultimate goal here would be to have everything look like the two top ones there, right? If we had all of them classified, that's a pretty good foundation for using this data to make decisions. But this part, or this one, no, this one is different. That's like, it's not one particular bug, right? It's some more vague grouping categorization thing. And if we go back to the rules file, because of that choice that I did, I just picked the top one, right? This is an ordered list. And if I put this vague thing here on the top, I mess everything up, because then we're back to the thing that I had with the automatic web service, right? All the crashes that I care about, they're the same thing. That doesn't work, but back then when I started doing this, I sort of just realized that, well, if I put rules for known issues at the top, and I make sure that they are high quality, meaning they're specific, so they only trigger when you have a case of that particular problem, then their order doesn't matter, because you have a crash report. It is only one bug, right? So only one of them will trigger. So then I could keep the code simple, just pick the top one, and then at the same time, if you get down here, so none of the lists of known issues that you've got trigger, that means you know it's a new issue. And in that case, it can be very helpful to pull out some information, categorize them some way. So I made that concept explicit, and here in the minimalistic syntax, I just add 3 dashes to separate the two types of problems, like known issues, unknown issues. And I'm going to put a description here. So unclassified crash in video. And we can run it. So now you can see that there's a new color, orange, and it's starting to look a bit more clear. We've got a list of known issues and then some unknown issues. You can scroll up and find the stuff that are unknown issues so that you can take a closer look. But we still got this bulk of unmatched things. So I want to just bring in some more of these vague categorization rules so that you can see how they can often provide more information that you may have thought on like more than just categorizing like this. So I'll run this NX thing again. So refresh the editor. Whoops, wrong. And now we got some new rules here. You can see how simple and beautiful regexes can be. We've got this rule for unclassified jump in video, which searches first just for the same thing, that it's a video thing, and then this ugly, scary thing here, which looks complex because it sort of is. This picks up something from the logs that is really interesting, and it's when you read the logs, it's not really obvious. It's not so easy to spot. So basically what we've done here is that a person that is a domain expert for these devices and the logging and stuff like that has put that domain knowledge into this rule so that anyone that sees the results here will get sort of that information for free without having to know that. Yeah, and then well, that's the rule that we had from before. And another case here, unclassified assertion failure in main, just checks that it's a crash in main again. And then another regex, it searches for the word assertion, and it skips ahead and then failed. And here the interesting part is that the text that is skipped ahead of that is often basically describing what's wrong here. So if we run this again, see. So now you can see that there's a little bit better categorization here. And if we take a look up at these 3 crashes here, those are unclassified assertion failures in main. And you'll immediately see that this one and this one is the same thing. You can see sort of what it is, some account handler being started twice, and that this one is something else. So it's sort of, at that time back then, was helpful for me to just quickly screen things and work with these crashes. We can take a look at the illegal jump in video thing here. So here you can see that it picked up illegal memory access at and some address. And the interesting part here is that you'll find that address again down here, which is the program counter in the register jump. So that means that we try to execute some code from an illegal address. So that's, not so easy to spot and could be very relevant information for whoever needs to work with this. Oops. And then also in that rule, it had a little regex thing to pick up the top 3 entries in the call stack. So you can see that here. So that also you can provide helpful information like this. Of course, you can see the pattern here. And for me back then, I mean, it was really helpful. It seems pretty backwards still. You're going from a fully automated web service to script, where you have to write stuff manually to get stuff classified. But it turned out that at some point in time, I started to realize that this script running on my computer is starting to become the way we handle crashes at Lysaker. People would come to me with stuff they wanted to search for. I would run it overnight because there were many patterns and a lot more crashes, and the whole thing was just not sustainable, of course. So I went back to that web service and basically rewrote it to be based on this principle instead, and being semi-automatic instead of fully automatic, so that in that service people can add rules like this. And 10,000 commits later, it looks something like this. And as soon as this service first then became available to developers at Lysaker, the usage basically exploded. And since then, this is the way that we're handling crashes at Lysaker. And it has been working surprisingly well. We now call these rules signatures. And you might notice that this is the exact same data that I was working on in the terminal. So we got 2 rules for known issues. That would, in our system today, that would be like more like 4,000. So you get the gist here. So there's a section then for known issues, a section for unknown issues that more vaguely classify stuff together. Go back to the main page here. There's 1,000 things that we could talk about here, but that's not really the point. The point really is that this extremely simple algorithm and concept really has turned out to work really well for us. So I'll just show a very few quick things here. You can open up a section of crashes, so get some basic information for each crash instance. Here, for instance, you'll quickly see that all of these are happening on the quad camera system type. We're collecting like metadata, so you can see stuff like which software channel did it happen in, what sort of system types, stuff like this. you can filter and work with the crashes as you wish. Also, just quickly run through typical workflow for a developer that, or let me back up a little. What we want to do here, right, is to have as much as possible as known issues, right? So that we have that solid foundation that we know what everything is. So we want to move these unknown things over to the known things. And where you do that, menu here, add signature for these reports. So we've got 11 unclassified main assertions. And this UI is a bit jarring, but just bear with me. One feature that we've added among those 10,000 commits is to automate things, because writing those rules are tedious, right? So, but we want a real person to be involved and to sort of take ownership and see that automation is sufficiently good, because often, in many cases, it's easy, like in this case. It's added a suggestion then for this particular assertion problem, where this is the assertion text and this is the function that had the assertion. But many times, properly classifying these things, it really there's a need for proper domain knowledge. Like, often you'll actually need to go into the code and check some stuff there to be able to properly say which part of the logs are relevant and what they mean. You can scroll down here a little bit. This is now then the actual rule. So syntax is not so minimalistic anymore, but it's basically it's combining a regex search for this particular string, and then the call stack. And this is no longer regexes, because let's face it, regexes are not always great for everything. But we can test this, and it says that it matches 4 of those 11. You can commit it. Now it says that there's a bug here even. four of those reports that we had in the database here got reclassified to this new signature that we created. So now you can see that instead of 11, there are 7 left unclassified main assertions. And down here, we've got the new rule signature with those 4 crash reports. There's no Jira ID here because it's a new thing. So what you typically do is create a Jira issue. Then you'd have a new Jira issue, and those 2 would be linked. Yeah, so that's basically it for sort of demonstrating what this tool is and does. Up until now, just been talking about crash reports, but this simple concept and algorithm, if you can even call it that, it really works whenever you have a situation where something can go wrong and there are logs. And regexes are really flexible and powerful, even though they are quirky and sometimes cause more problems than cause more problems. Anyway, among those 10,000 commits that we've done since then, a huge chunk of it came when we set up a little team. Thomas joined, and we decided to rewrite the whole thing from scratch, from a crash report tool, like very dedicated for crash reports, to a completely problem agnostic tool for failure analysis. So now Thomas is going to talk about test failure analysis with this concept.
Hello, can you hear me? Yeah, good. So in order to talk about tests, I want to talk about it in the context of an internal role we have at Lysaker called the build master. So Jan showed early in the talk the continuous integration pipeline, where we have this latest channel where we push daily releases for internal use. And the build master is responsible for for getting software onto that particular channel. And in order for a commit to get out into that channel, it has to pass a myriad of tests, quite a lot of them actually. And if something goes wrong, it's the build master's responsibility to make decisions. So sort of in short, the build master is like a shepherd, and the sheep, I guess, represent tests or developers, depending on their mood. And so when a developer pushes a commit, that commit will run on a CI machine, doing some unit tests and stuff like that, and some basic sanity testing, validating that it's not completely broken. And very quickly, if it's not broken, it will start running on our integration tests, running on actual hardware and infrastructure. I've heard that we run about 60,000 integration tests every day. And that's a lot of testing, and it's a lot of moving parts. And the likelihood of a single commit just passing through the entire test pipeline and nothing going wrong is like 0. So that's the need. That's kind of why we have the build master, because the build master needs to figure out what is going wrong and make decisions whether or not it's appropriate for the things going wrong to be ignored, or if it has to be followed up, meaning that we choose another commit. So when I started at Lysaker, the build master role was sort of like this. I don't know if it's the greatest illustration ever, but in the middle there, at the center, is the build master. And the build master every day would sort of open up a commit, get like a wall of red failing test results, and have being sort of tasked then to figure out what's the state of this commit. And that sort of, you have these problems, and you have people you need to talk to about those problems to figure out what to do about those problems, because things are so complicated. You need to talk to domain experts that know the tests and know the part of the code that's affected by the problem the test exposes. So the arrows are sort of overdone because the entire thing is very heavily weighed down by this sort of I'll get back to you style of communication, where, okay, me as the build master, I see the problem, I send a message, and maybe I'll get the response of the message immediately, maybe in an hour, maybe at the end of the day, or maybe it turns out that person is sick or on vacation. And it's sort of, when you're dealing then with 20 simultaneous problems, you need to sort of juggle many things and be on be on the ball, which isn't like an English expression, but essentially you need to constantly remember what the state of each problem is, and make sure that you're like, if it's taking too long, you need to call that person. And at the bottom there, you sort of have the managers, and the top there, it's supposed to represent developers. I forgot to say that. And the communication, like the point of the communication is to get this total picture. But sometimes it breaks down. The managers might actually sit on information that is relevant to the commit that you're sort of trying to get these developers to sort of tell you about. But it turns out you shouldn't really be pushing for that commit because they know, like someone told them something, right? So it's not great. It's not conducive for daily releases. But a while after I started, there was an internal push at Lysaker where they saw what Jan has made, like it was popular, it was under heavy use, and they saw that it worked. And they wanted to see if we could use it for failing test results as well. And it's outside the scope of this talk to talk about what we did. It was a heavy investment, as Jan mentioned, with many improvements and tight integrations into our test tools. So, as I mentioned, or I'm getting ahead of myself. Essentially, the point is it turned out really well, and now it's like a central part of what we do. So instead of being like every morning, you're no longer exposed to like a huge wall of red failing tests. Instead, you are exposed to a huge wall of red failing tests with a description of what's going wrong, and thankfully a Jira that will like sort of tell you how serious it is. So here you see, like this is an actual view from one of the tools we use for our test pipelines. So on the right-hand side, you see the integration with our pattern matching service called TFAT. It's the one we use for tests. And it has the description and the Jira, and you can click it, of course. And you see that it's finding the same problem across a multitude of different whiteboarding tests, which is great because it's the same failure. I don't have to call anyone or talk to anyone. I get all the information in the Jira. And this is like up to date. It's recent. It's something that has just run. And no one's necessarily looked at it because maybe the signature already existed before we ran this commit. Yes, so this is one example of why this has worked out so well, is that this drastically reduces the communication that we need to go back and forth, speeds everything up. But another reason, which Johannes also touched upon, is this idea of the flexibility of the regexes. Because it turns out that classifying tests, running these giant integration tests, is in many ways a more difficult problem than just crashes. In crashes on a single device, usually the context is very well known. It's usually like it's the software doing something fundamentally wrong. It's usually something you can derive from the logs themselves without any other context. But with test integrations, the problems can be very indirect. It can be there's a router that's broken, it's infrastructure problems. It's not always obvious why something goes wrong, and it's not necessarily true that you can just find some log lines on your device that tells you exactly what's going wrong. Maybe there is nothing in the logs that could tell you what's wrong. And to illustrate this point, I'll talk about something that happened when we released this device or started developing on this device, or sort of closing in on when it was going to be released. So this is the Desk Pro device, which is a personal video conferencing device that sits on your desk, obviously. We, of course, put it in our test automation lab, just shove it in the shelf, and it starts running in our test orchestration scheme. And very soon after, we started getting tests that would fail with no outgoing video. And that's pretty serious. Like that's if there's no outgoing video, that's a pretty serious problem. But turned out it's not that big of a problem, because what's really like the issue was not necessarily related to the software. So at the top of this device sits a camera, and that camera has a physical privacy cover. And you just flip it, and then it will physically block your camera, because customers want this. They want the sort of the peace of mind of being absolutely sure that we're not watching them. We aren't, of course. But turns out that lab engineers fiddle in these shelves, and cleaning personnel dust in these shelves. And the thing they have in common is that they all like to sort of accidentally push the privacy cover shut. And then you don't get any video. So now you have a shelf where some of the devices have this shut and some of them don't. And the test orchestration will then pick them without paying attention to this, of course, and random tests will fail. And you will have engineers being like, why is this failing? Because they will focus on it because it's a serious problem, right? So normally you'd sort of say, well, how would you communicate this? And you would should you send a mail and tell people about this and just be like, well, you need to be mindful when you're analyzing your test results that this could potentially be the thing that's happening. Well, no, because now we have this integration with the pattern matching scheme. And as you saw, we have sort of the communication bit where descriptions and such are propagated to other tools. So what we do is that once we figure this out, someone will then create a signature that looks for any test that fails with something related to video problems, and the privacy shutter is shut. And they create the Jira. Jira, of course, explains what's wrong, and that is propagated to absolutely every developer that runs into that particular problem. So they'll have the description when they're looking at the red test and say, well, this has a Jira and everything. I don't have to look at it. I don't have to look at the logs. And you save a ton of work. You don't have developers running around chasing nothing. So fundamentally, doing this test integration thing has really changed the communication style in our testing pipelines and contributing to our ability to deliver daily releases. You no longer have many instances of having to talk to a lot of people. Maybe they're not available right now, because people are now very motivated to create these signatures and Jiras. So you saw the example of the sort of the build master view. The reason why that works is because that information is stored somewhere. It has a Jira, it has a pattern. And essentially you end up with these sort of problem data blobs, I'll call them. Because the combination of Jira, like people are familiar with like bug tracking and such, like it will give you a description of what's wrong. But when you combine it so that when you click on the Jira, you can click further and get just a list of everything that has failed or crashed due to that particular Jira. It means that you sort of have all the information in one place and it's constantly kept up to date. So you not only do you know what's wrong, you get more or less instantly an impression of the scope of what's wrong or the impact of what's wrong. So that has really motivated people over time. It has shifted the culture where people are motivated to create these data blobs and be thorough. It also means that communication, like it's not only for the build master that communication has changed. It's true for managers as well, because they can look for particular Jiras that are really serious. And those Jiras, of course, are kept up to date as well. So they can look for particular like serious Jiras in software that is considered for customers. As well as for support. Like we have customer support, and they'll get logs from our customers, of course. And instead of having to contact engineers to get help, they'll usually just post those logs against our pattern matching service and get Jiras back. So most of the time, they're not interfacing with the engineers. They're just posting stuff against this pattern matching scheme. And for the developers at the sort of at the top there, say I, as a developer, make a mistake, and I know that I'm going to cause a lot of noise in our testing pipeline. I'll upfront create a pattern matching regex and a Jira, and then I know that even though I know it's going to propagate through our testing pipeline, everyone affected by it will be informed immediately, so they don't have to look at it. So again, it's this sort of almost instant communication by putting everyone or everything in one place, which was sort of the problem in the first sort of iteration I showed you of this, where you don't want the single person to be like responsible for containing all the information about the single commit. So that's kind of the story about how we or sort of the end result of our testing effort. So if you're still wondering, like, again, this seems a bit insane. Like, are you really suggesting that engineers should spend their time writing these regexes, this like old-fashioned pattern matching thing? Like, that doesn't seem like a good use of time. Well, it is, right? That's what we're trying to convince you about. But like, you might say, well, you know, could you not automate more stuff? No, because like these problems are difficult, like especially the test stuff. It's like, I don't know if you could create trivially an automated tool that would allow you to automatically detect the privacy shutter connection. Like, you need to understand, like, that still requires human knowledge, at least today. And another thing that becomes a problem, like, we've had attempts at automation. Like, we did some stuff during like the machine learning craze and all that, where we tried to do some clustering and stuff. And like, the problem that very quickly came when we started trying to expose people to it is, why does it make the classifications that it's doing? And you can't really tell them why. Like, probably if you spend a lot of engineering effort, you could make algorithms that have a lot of introspection. But with regex, that problem, like, it's obvious why it's doing the thing it's doing. And it allows for accountability, like where you can go back and say, well, it's classifying a lot of stuff. Why? And you can see, and you can, like, if you're a domain expert, you can sort of make a judgment call. Is this a sensible thing to be looking for this particular problem? And this again inspires like trust. Like, you trust that because every single signature is made by, like, as Jan showed, it's like we have some automation, but we didn't fully automate it. And the reason for that is that when we did, people didn't pay attention, they didn't follow up, because they didn't trust. Like, it's partly that they don't trust it, but partially too much stuff going on, that or too much noise, essentially. And if you have a person saying this signature is okay, you can always refer to that person, and there's sort of automatic ownership of that particular problem. Yeah, so maybe in the future we'll have like a machine learning or AI thing helping us doing this stuff, but it doesn't seem like we haven't seen anything yet, and we don't know if we'll have anything soon that would be fully automated. But as we also shown, like, if you're in doubt, like, this is what we use. There is nothing else at Lysaker that we use for crash or test classification. This is the algorithm. This is like the super simple ordered list regex algorithm, and it scales. Like, it handles our entire cloud deployment. Like, every crash that comes from our devices in the cloud is sent to that service and analyzed. So it's at least it scales for our purposes, and I don't think there's anything indicating that it won't scale at least a tiny bit further. So yeah, hopefully you found this interesting. Thank you for your time.